Good day, everybody. We want to show that the square root of this rational number, which has a peculiar looking form, actually turns out to be a rational number. And of course, a typical member of Q looks like this, m over n. Okay, where m and n are integers. Okay, n can't be 0, of course. All right. Now, this is a sort of a famous result. In Ramanujan's name has been associated with this expression where he was able to write the Radicand as a product, or the whole thing is a product of rational numbers, which proved it's rational by a factoring process. I have just a more arithmetic approach here. Now, a couple of results I want to write down that are very, very useful is the well-known quotient rule for square roots. It says the square root of a quotient is the quotient of the square roots. Okay, meaning this. Square root of A over the square root of B. I'm sure a lot of you have anticipated why that's important, or see why it's important right now. And also just the square root, let's call it just A raised to the 2k, where k is a positive integer. This is just equal to a to the k. Okay. These are the two main results we'll be using to get this problem solved. And know that there's an understood index of 2 right here that gets left out all the time. Okay, so let's move along. Now, the very first thing I do is just take our Radicand, this blue object, and 1 minus 1/9 is 8/9. 1 minus 1 over 49 is 48/49. And you can see right off the bat that the denominators are all perfect squares. Okay. So we can go along here and just do that. We took the square root of all of this stuff, and see how we took the square root of 9, square root of 49. It's based on the rule up here. Square root of the quotient is the quotient of the square roots. Now, so we got 3, 7, 11, and 19 from 9, 49, 121, and 361. So this much is true. And so all we have to do now is just find the prime factorization of this to show that it's a square integer. Okay, that's the approach I took. And notice we won't actually produce an actual. We're just going to show it's a rational number. We're not going to actually find what that rational number is, which I like. So this is 2 cubed right here. 48 is 3 times 2 to the 4th. That would be 3 times 16. Now, what about this? This is equal to 8 times 15, which is 2 cubed times 3 times 5. And what do we get right here? 36 times 10 is 36 is 2 squared times 3 squared. So, and then 10, so you would have 2 cubed times 3 squared times 5. You see, this is where all the computation is going on. All right. Now, if you take that product, if you consider that as a product, and I'll just come out here like this. Okay, what are we getting here? We have, and let's double check. Did I get all this right? This is 8 times 9 is 72. 5 times 72 is 360. 8 times 3 is 24, times 5 is 120, and this looks right here also, 3 times, yeah, okay. So, y'all, what I'm going to do is just try to keep track of all these exponents. We're going to have 2, and what do we have here? 3, 7, 10, let's see here, 2 cubed, oh, wait, sorry. We're going to have 2 right here, 2 to the 4th, 2 to the 8th, 2 to the 11th, okay, and then I'm getting 2 to the 14th, folks. And y'all, you can double check that for me if you don't mind. 2 cubed right here. Another 2 cubed right here is 2 to the 6th. Okay. This would be 2 to the 10th, 2 to the 13th, and 2 to the 4th. That looks right, okay. So let's do 3. Now 3, it looks like we have 3, 3, and 3 squared, which is 3 to the 4th. Right, folks? it's all we have left is 5s. Okay, we have 5, so we have 5 squared. Now you see we have that exact thing we're talking about. All of these are even exponents, right? And so when you square root this, you're just going to get, and also I didn't write down, you can split the radical apart also. This would be 2 to the 7th times 3 squared times 5. So you see, that is an integer, right? This object, well, yeah, I'm just showing you this for show, but we know that this is an integer, so this top part is an integer. I'll just put a member of z, or we'll say of n, right? And so it's QED time. We've shown it's the ratio of 2 integers. We've just shown that this top part is the ratio of 2 integers, or is an integer, which means this whole thing is the ratio of 2 integers, right? So QED. And again, some of you may be thinking, well, why didn't you just tell us what it was? You don't need to. Because remember, the explicit instruction said to show that this is a member of Q. Well, at this point in time, we know it's a member of Q since this top part, the numerator, resolves to a natural number, and the denominator is certainly a natural number. Okay, so we are finished with the problem. And again, I got this from one of Ramanujan's many identities. He actually managed to figure out a way to write the radicand itself as a product. I don't know how he did it, but he did it. The way he did it was harder. I mean, it was more elegant and nice. But this is just a brute force bunch of arithmetic that I did right here. But anyway, that does it, folks. Thank you for viewing.